So, Ozzy, how's it going with making sense of that stuff about the building blocks of matter? Getting there? Well, not really good. I'm getting a bit confused. There's stuff about elements and substances and atoms and nucleuses and protons and atomic numbers, and I can't seem to get a good handle on any one of those without understanding something about at least some of the others. Well, that's a good observation. An understanding of every single concept in chemistry depends upon understanding some other concepts. I sometimes think it's a bit like introducing someone to a video game or a board game like Monopoly. Where do you start? You can't learn the rules without reference to the structure of the game. You can't learn strategies without knowing something about the rules of the game, and so it goes on. So actually we don't learn any component in totality at first. We come to understand by learning enough about this part and about this part, sort of partial knowledge about lots of bits growing as we need more bits to support other bits. Imperfect knowledge, imperfect knowledge, all the way. And so it is with chemistry. We can't learn any idea in totality without understanding at least partially other ideas. Everything is interdependent. Okay, that makes sense. Can you explain to me how things interconnect in this area of chemistry? Well, I can try. I'll give you a sort of framework that shows the relationships. But don't expect to understand the ideas fully now. We'll focus on particular ideas deeper as we go along, okay? All right, so where do we start? Let's start with some pretty basic knowledge that shows what depends upon what for now, what's at the heart of everything. And I suppose we can start by saying that all matter consists of atoms, tiny, tiny, tiny particles, much, much, much smaller than we can see even with a microscope. So I'll represent an atom as a circle, way, 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 magnified, way, 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 way. In the centre of each atom is a nucleus. Again, very much tinier than even the atom. And the nucleus contains protons, more particles, and they've got a positive charge, and neutrons, which have got zero charge. And then surrounding the nucleus are a number of electrons. And it's best to think about electrons as some sort of a smear of stuff, of charged stuff. They've got a negative charge. But rather than thinking of them as dots, tiny particles, it pays off in the long run. Think of them as some sort of sphere. Now, of all the naturally occurring atoms, there's some different types. For our purposes, about 90 different types. What do I mean by type? I mean from one to one, from one type to another, they differ in the number of protons they have. That's the key difference. And all of the atoms that have the same number of protons are said to belong, number of protons are said to belong to one element. Okay, that's an absolutely fundamental part of where we're going. Can't go anywhere in chemistry without that. During chemical reactions, the atoms of an element might change partners, what they're combined with, but they always retain the same number of protons. They can't be destroyed, they can't change into atoms of other elements. So, in a sort of circular way, coming back upon myself, I can say that an element is characterised by the number of protons that its atoms have in the nucleus. Okay, so just thinking aloud, Prof, is there one particular element whose atoms, every single one of them, have got just one proton in the nucleus of those atoms? Good work, Ozzy. There is such an element. The number of protons is 1. If the number of protons is 1, we say the atomic number, for which we use the symbol, is 1. And that particular element, the name of the element, is hydrogen. You've heard of that. And the symbol we use for the name of the element is H for hydrogen. Okay, good. Didn't introduce this to you before. Atomic number is another word for the magnitude of the atomic number, is another way of saying how many protons there are in the nucleus. Huh? Great deduction. Any more elements? Well, I guess there are lots and lots and lots. What do we choose? There's got to be an element such that every one of its atoms has in the nucleus 8 electrons. You're right, there is such an element. 8 electrons. The atomic number is 8. We call that element oxygen. And the symbol for the name of the element is O. Any more? Okay, I'll get adventurous. I'll go for an element of which the atomic number is 100. Well, there is such an element. It's called fermium, but that's not naturally occurring. It's been produced in a laboratory, tiny traces of it for tiny duration of time. Anything beyond 92, atomic number 92, is in the realm of nuclear chemistry, artificially produced. We'll focus on those up to 92. So, for example, I'll just give you a couple more of elements that you'd be familiar with. An element which has every atom with 11 protons in its nucleus is called sodium, and one with 17 in its nucleus is called chlorine, and so on. Roughly 90 odd of them for our purposes are useful. Now we'll refer later on to tables, the tables of all of the elements, and in particular an ordered arrangement in a table called the periodic table. Got it? Let me just check. Elements are defined by the number of protons in the nucleus of their atoms. Well, that's a current day definition, Aussie, but just a reminder, the elements as substances had been identified and their properties studied long before protons were even known about. So they originally weren't identified by the number of protons in their atoms. They were identified by observation, by measurements, by chemical behaviour, by physical behaviour. So I'm presenting a view of elements and atoms from a current knowledge viewpoint. Now, a little bit of language and communication, Aussie. If I said to you the word oxygen, what would come to mind? Easy. I'd say atoms with 8 protons in the nucleus. Easy. Well, you're partly right, but there's a whole pile of other meanings of oxygen. Oxygen is the name of oxygen is the name of an element. Okay, just a name. Just like your name's Aussie. But it also refers to the atoms of the element oxygen. So we might use O when we're using chemical equations and which atoms have done what, we would use O to represent those atoms. In the atmosphere, there are oxygen molecules, thank heavens. And those oxygen molecules are composed of one oxygen joined to another oxygen. And so we write O2, and that's one meaning. Another meaning of the word oxygen. And then again, there's the stuff, which is oxygen, composed of these atoms. There's the stuff which has mass, which has certain properties. It's oxygen, and at ordinary conditions, it's a gas. So we write for that, the symbol for that. The molecules are O2, and it's a gas. This indicates that we're talking about a substance, not the molecules, or the atoms, or the name. All right? Different meanings. So we have to be pretty careful when we're using the term oxygen to be precise and make it clear which of these meanings we're using. Otherwise there'll be stuff-ups. Exactly. Absolutely must do. Yeah. Now, I want to make sure you realise the importance of some ideas that we're not going to take any further today, but are part of this big framework about the nature of matter. And we haven't paid any attention to, we focused on the number of protons in the nucleus of atoms. We've paid no attention to neutrons, which are important. They have a negligible effect on the chemical properties of an element, but they do affect the mass of the atoms, and they would give rise to isotopes, which you've heard of, I'm sure, and we'll talk about more in future. And the other one we haven't talked about, is the electrons in atoms. In uncharged atoms, the number of electrons is equal to the number of protons. The chemical behaviour of the elements is almost entirely dependent upon the energies of the electrons in the atoms, especially the ones with the most energy. And we'll talk about actually what that means in another tutorial. Okay? That's a lot of stuff you've talked about in this roadmap you're creating. Prof, is it all really important? Well, what a question, Ozzy. Is it important? The molecules of every substance that exists consist of some combination of atoms of only 90 elements. And yet every substance is different from every other substance. Remarkable. Every substance that exists consists of some combination of atoms of only the 90 elements that are naturally occurring. So, for example, I have this board that I use frequently when I'm talking with people like you. These are the first 12 elements, atomic numbers 1, 2, 3, 4, to 12. And if my board was big enough, I'd go up to number 92. And the point I was just making about every substance consisting of some combination of atoms, for example, water molecules. Every molecule of water has 2 atoms of hydrogen, none of helium, none of lithium, none of beryllium, none of boron, none of carbon, none of nitrogen, 1 of oxygen, none of fluorine, none of neon, none of sodium, and none of magnesium. Every molecule contains 2 hydrogens and 1 oxygen, which is why we write its formula as H2O, where with no prefix signifies 1. Okay? Carbon dioxide, none. It has 1 of carbon and 2 of oxygen. It's a little bit out of line there. So its formula is CO2. Butane-1-ol, compound you're going to become quite familiar with, has got 10 hydrogens, none of these, 4 carbons and 1 oxygen. So it's C4H10O. Okay. Can you see we can get all sorts of combinations and myriads of molecules, even in our imagination, but in fact, in reality. Diethyl ether has 10 hydrogens, 4 carbons and 1 oxygen. You're getting the idea about the number of possible substances, compounds as we call them, there are from the combination of atoms of such a few elements. Prof, you've stuffed up. This is the same as that, and you've given them different names. You must have the composition of one of these wrong, because you've got them the same. So they've got to be the same substance. Well, you might have guessed that I did this deliberately, Aussie. These 2 compounds do indeed have the same combinations of atoms of 3 elements, 4 carbons, 10 hydrogens and 1 oxygen. So they're the same? No, they're not. Different atoms are joined together in different sequences in this compound from in this compound. Let me get rid of this and find a bit of board space if I can. Butanol is carbon, 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 OH, H, H, hydrogen, hydrogen, carbon, hydrogen, 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 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 4, and 1. But diethyl ether has a structure carbon to oxygen to carbon, and now hydrogen. I'll just draw sticks to the hydrogens, and carbon. If you put a hydrogen on the end of these sticks, things are joined in a different way. They're entirely different substances with entirely different behaviour, chemical reactivity. So, in fact, there are many ways in which the arrangement, not just the number, the arrangement of atoms in molecules with the same composition can differ. What's joined to what, or how they are arranged in space. And we'll be talking quite a lot more about that in the not too distant future. But it's astonishing that every single stuff is based on some combination of atoms of only 90 different sorts. Right? Whether it's substances of simple molecules, like water and what's on the other board, and carbon dioxide and the like, or whether it's large biological molecules or biological polymers like DNA strands, or new materials, or new medical reagents to cure cancer, whatever. Every single substance, naturally formed or formed in laboratories or in industrial factories, is composed of some combination of atoms of only 90 elements. That's astonishing. That reminds me a bit of a discussion we had around the family table at home last week, where we're talking about people's faces. I've only got, say, 10 characteristics, a couple of eyes, a couple of ears, a chin, a nose, a forehead, eyebrows, and yet every person can look different from every other person of the 7 billion people on Earth. It's amazing. And this sounds a bit simple. Yeah. But I'm digressing. Anyway, it seems to me that nothing you said about atoms and elements and stuff seemed too difficult to understand? Thanks. Good, Ozzy. But as I said before, you've now got only a partial understanding of a few things. And you've got some idea of the relationship between them. You've got a roadmap to make further learning easier. Okay? All right. See you next time. Yeah, good. Next. Come in.